right. Thank you for being here. And let's start with the usual. Hi, I'm Benjamin. You can find me wherever you want. While I'm here, you can also call me if you want to chat, shoot me an email. We'll find a place to discuss stuff. Mostly I'm a jack of all trades, master of some. I do some DevOps, security, some embedded stuff. And about 7 years ago, I took a look at AMD K8 and K10 microcode and also talked about it on the C3 back in Leipzig then. And currently I work at Grab Nebula. We mostly do some Tauri stuff, so come talk to us if you're interested in that. Opinions are still my own and mine only. Please don't blame my employer for any of that. All of what you're about to hear is reverse engineered. There's a huge amount of guesswork involved, and probably things are very wrong. If you break your CPU by using this, it's your own fault. We haven't managed to do it. If you manage to break yours, let me know. It would be kind of interesting to figure out how you did that. And if you happen to be an AMD engineer that worked on this, I'm really sorry for what I'm about to do. You did a great job, and I'm going to stomp all over it. So we're going to start with a very fast background. I'm going to show you the tooling we implemented, show you some actual microcode in text form. I'm going to show you how we got the microcode RAM out of the actual CPU, and demo, most likely not. Speedrun. The highlights are complex x64 instructions are translated to internal instructions via the microcode decoder, stuff like readmsr, wrmsr, that's microcoded. You can think of the microcode decoder as something allowing something like code execution. You're not correct, but you're not wrong enough for it to matter. Microcode updates can be forged on Zen 1 to Zen 4 CPUs with known keys and tools. And if you apply a microcode update, you actually replace stuff in the microcode ROM with new things that you supply in the microcode update, and this happens via match registers, which I also sometimes call hooks. Microcode instructions that you can supply via the microcode update, they allow arithmetics, memory access, load store, and some conditional control flow. When we started, we wanted to get started with our own stuff before Google released the Zen tool. They've, of course, figured out the entry sign on which everything you're going to hear is based. But, well, we wanted to start before, so we got to work. From our work on AMD K8, K10, we had AngryUEFI, but it's a bit dated by now. So we wanted to keep it as a low-noise environment, essentially control every instruction that gets executed on the CPU. Drive execution from a different PC, and report back the test results to this PC. What we wanted to improve is, well, maybe we should start using network instead of serial ports, especially because we can't use USB-attached serial ports, only those native to the mainboard, and try getting an AM4 and AM5 mainboard with a native serial port. Should be reasonably easy to expand. AngryUEFI were more or less single purpose, but AngryUEFI is a bit more amenable to be expanded, which was pretty nice because I had to add a lot of stuff. And should also be reasonably easy to build and deploy. I distilled it down to like 3 shell commands, and then it works. Also, it should be able to recover from most failures. For example, we are throwing random microcode at the CPU, it's going to page fault, it's going to throw general protection faults. And the more often we can avoid rebooting the entire system, the faster we can run our tests. So AngryUEFI, as the name I suggest, is a UEFI application. I did that because UEFI usually ships with a network stack, so it's up to the mainboard vendor to implement it, and I can just use it via generic APIs. I don't need to worry about network drivers at all. You boot it from a USB, like a basic OS. It's not an operating system, but more or less it does the same. It has multiprocessor support. In UEFI lingo, anything that is not the boot core that is started automatically by AngryUEFI is called an AP. And on these APs, we only run our instructions that we supply. UEFI doesn't actually touch it. It also has a TCP server, and this thing runs on the boot core. You can test on the boot core. I would recommend against it, but essentially the stack runs on there, listens for incoming commands, drives test execution, reports results back. In essence, you actually get asynchronous test execution on the IPs. If you have, for some reason, a test case that takes 5 minutes to run, and you have a 6-core CPU, you can run 5 of them in parallel and query via the boot core what the current status is of each. APs can recover from essentially everything that leaves the stack somewhere in writable memory. They won't try to continue test execution. Instead, they just write error information and wait for the next job. Currently, the APIs are implemented or applying microcode running x64 code on the core you just applied microcode to, and I also implemented some higher level APIs via Angry Service Returns, ASRs. Think of them as basic source calls. What I currently have implemented is instruction-based sampling, which is really nice to figure out some microcode internals, and DSM, which I sadly can't show you much, which is even further, which provides even further insight into microcode execution. It's open source, you can find it on GitHub. Feel free to play around with it. Let me know if something breaks or you find something cool with it. To drive execution, we have a Python framework that runs on the client, and it connects via TCP to AngryUEFI. We also have basic database in there for test setups that track stuff like, okay, this is Zen2, this is at this IP address, this has this known quirks, like the power LED doesn't work because I can't solder. It has a really high-level API. Essentially, this is a microcode I want to run, this is the machine code I want to run, throw it on any core that's currently free. That works for like 90–95% of test cases. If you need to drop lower, you can go all the way down to build your own network packets, throw it at it, and parse the incoming network packets. Usually, you shouldn't need to do it, but if you need to. I also integrated with ZenTool from Google, which we still use for signing, and also with ZenUtils, which is our own custom assembler, disassembler, macro assembler. I cover that later, so you can just write text and it handles everything in the background. It also integrates with our power control, which I'll show you quickly, which is just a way to kick over a setup that doesn't respond to network requests anymore by just pulling the reset pin. Again, up on GitHub, feel free to play around with it. It's mostly vibe coded, I'm sorry. This is a power control board. This is a third iteration. It nearly works now. Essentially, just hook it up to an ESP. It talks to my Home Assistant instance, and you can just reset the setup, power down, power up a setup with it. So our flow is you connect via network from AngryCAT to AngryUEFI. AngryUEFI connects to AngryESP via some jumper cables to the system pins, and Home Assistant talks to AngryESP via Wi-Fi. This is Zen 5 and the Zen 2. Zen 2 usually served as my development platform, and as you might notice, it's a bit of a chaos, which at some point I got every test setup we had together and just stuffed it into some casings. We have Zen 1 to Zen 5, all available and connected, and we can run tests on each of them. All of them are hooked up to AngryESP. To boot AngryUEFI on your own system, enable the network stack in UEFI. UEFI usually, well, some UEFIs have a setting to enable IPv4, IPv6. If they don't have it, enable LAN boot, and that way the network stack also gets enabled. You should disable SMT or hyperthreading in Interlingo because SMT siblings actually share the microcode updates. So if your boot core is core 0 and you run a test on the core 1 and you apply an update on core 1, you're actually applying that to the boot core as well, which is going to cause chaos. Disable it is my recommendation. AngryUEFI currently requires a GPU, so it can output some stuff onto the terminal. I haven't fixed that. It's not strictly required, but just grab a 10 euro GPU off eBay. Some GPUs, again, need an attached monitor for them to work, but they are dummy HDMI plugs that just say, yeah, I'm a display. Then grab the USB image from GitHub or build it yourself. You don't trust the USB image you download off random GitHub, and flashes on the USB key, boot from USB. AngryUEFI is going to grab an IPv4 from DHCP. It tries to print it, which usually doesn't work, depending on the mainboard. So just check in your DHCP server and give it a static lease. And at that point, throw test cases added via AngryCAT. ZenUtils, my North Star of this project is become the new bin utils for my Zen microcode. Currently, we have a single-line assembler, so you just give it one instruction, it gives you back the binary that corresponds to that instruction. It has a disassembler. You can actually wrap it into some Python code for it to disassemble an entire update or disassemble the entire ROM if you happen to have that. It also has a macro assembler with label support, all that good stuff, which is what I commonly use when I write stuff via AngryCAT, just because I can just write the microcode without worrying about relocations, slots that are blocked by metric registers, stuff like that. It also contains some YAML architecture definitions. We use a common Zen base, and then each Zen architecture gets a derivation of it because they actually vary in what they support. For example, Zen 1 and 2, 3 and 4, and 5 They are similar between 1 and 2 and 3 and 4 and 5, but quite different between 2 and 3, for example. For example, Zen 3, you need to worry about a few bits in the higher part that seem to be related to the execution unit you throw that instruction at. Not sure what it actually is, but you need to do the right thing, else it won't work. Also, the update size varies between generations. Zen 1 has only 64 quads. Quads are a package of 4 instructions and 1 sequence word that controls execution. And Zen 3 expands it to, I think, 128, and Zen 5 is huge. We still rely currently on ZenTool for signing, not because of any particular reason, just haven't gotten around to implementing it, and ZenTool does this just fine. I also added a Python API that I use via AngryCAT, so we can just script everything, you don't need to call out to it via shell. And again, up on GitHub, play around with it and have some fun. There are also examples both for the meshing code you can use to run updates and the updates itself. You need to worry about if your CPU matches what we have there, because there are differences between individual CPUs, even within a Zen architecture series. And now we can actually look at some microcode examples. It might sound fairly simple, but C string length actually shows off some really neat features. So this is macro assembly. You start with some directives that tells the assembler, hey, I'm assembling for a Zen 2. And some additional fields. The revision is actually important. The lowest byte of it is read by the CPU in order for it to determine if it should apply this update or not, because it only accepts updates that are the same or one revision higher, or multiple revisions higher than the one that is currently loaded. I'm not sure if it's a bug, and it should always accept only higher revisions, but if you want to make sure, just set this to FF and it will always work. The rest isn't actually parsed, but it's good to have it there.
Can you zoom in a little?
Sure.
Thank you.
Better, worse, for?
Perfect.
Okay. This essentially takes the buffer pointer to the C string in rex and stores the length of this in RBX. And we execute it by hooking a specific instruction. We tell the assembler for the match register slot null. Match registers define which addresses in the microcode ROM you hook, and then what is there gets replaced what you supply in the microcode update. And in this case, we say match register 0 for slot and 0420, which corresponds to shift left double, which is an instruction nobody really uses, but we really like using it just because Linux kernel, for example, doesn't really use it, so you don't crash Linux if you change it. And then you can just start writing assembly. For example, we just set our counter variable. Rec15 is not R15 from x64. It is an internal microcode register that is not visible to the outside world. There are 16 in total. Everything below Rec7 is special use and requires some care to use. So everything Rec8 and up usually is fine to use. Then you can see that we support labels, which is really nice for loops, and conditional branches. And then we do a load. And you can also see that you need to specify how wide the load should be. By default, it does a 64-bit load, but of course, you can drop it down to a byte in this case. We load it into another temporary register. And this is a segment annotation. Microcode supports all your standard segments you're used from x64, data segment, stack segment, but it also supports physical segment. For example, you can bypass address translation entirely and directly read and write physical addresses. In this case, we're using LS, logical segment, which means do the normal address translation. Then you just load from the address specified in Rec15. There are some implicit arguments here, a Rec0, which always reads a 0, and a displacement of 0. Then we want to set the 0 flag because we want to detect if it is a 0 byte. And this again requires an annotation. This means that the 0 flag inside the microcode engine. You actually have a 0 flag inside the microcode engine and the x64 0 flag. And you can say which one should be set or read. We write to Rec0 because we are actually not interested in the result, just in the flags. And of course, Rec14, which contains what we just read out. Then conditional branches, as you would expect, you have the standard mnemonics, but you also need to pay attention. You need to tell the microcode engine which flags it should read. Just because you're doing a jump equal, jump 0, it doesn't automatically also read in the 0 flag. So you need to annotate that. If the jump is taken, we go to end, but if not, we just increment our current data pointer branch via sequence word back up to the loop. But if we take the branch, we just store the difference of our start position and our current position in RBX, and that is, of course, the length of the string, and then we tell the assembler to emit the sequence complete. Sequence complete is another sequence word that controls the behavior of the microcode sequencer, and sequence complete means I'm done decoding this x64 instruction, and please get me the next one to decode. And for something a bit more complex, this is a Subleq implementation. If you're familiar with isolength, this is a Turing-complete computer architecture that only uses a single instruction, and that means you can actually omit the instruction, just need to specify the 3 arguments, which are 2 memory locations and 1 jump location if the result of the difference between the 2 memory locations is less or equal than 0. Again, classic directives. This time we are actually writing for Zen 1. This might be F course or Shift left D on the CPU. I'm not exactly sure, but it doesn't really matter. Then we have just some basic documentation, what registers we use. And then you can see a more complex version of the load. We just load in the start. Actually, this is a core context, which is a feature of AngryUEFI. Every time you go into the machine code AngryUEFI runs, it sets rugs to the address of the core context. And inside the core context, you can find all manner of internal information and pointers of AngryUEFI structs. In this case, result buffer, which gets returned to AngryCAT when you're done with the execution. So the first entry just means RBX now points to the result buffer. Then we do some basic initialization, 0 sum registers, and then we enter the actual loop. I'm not going to go through every instruction this time, but just as an example that you can actually write fairly complex programs. And the great thing is this is a Turing-complete VM, so if you really wanted to, there are cross-compilers, and you can actually run your code inside a microcode VM that only is 1 single x64 instruction on the outside world. This also, you can see you can set multiple flags. Currently we have the carry flag and the 0 flag. Most likely they are a little bit instruction dependent, but we're not sure about that yet. And we also have all 16 variants of jumps, including never taken jumps and always taken jumps, which can be useful for some stuff. We also have a custom extension to Subleq, which means if the jump destination is -1, it actually exits the Subleq VM, stops decoding, so we get control back in AngryUEFI and can report our results. And just to show you what this actually looks like, I can show you the machine code that corresponds to Subleq. This is just your standard x64 instruction. You can see we set up a memory buffer. It's done via instructions just because the x64 assembler we use inside AngryCAT doesn't actually support data fields, but this is just setting up some data fields. And this is the hooked instruction we replaced. So this runs your Subleq VM. And after that, you're done, and it returns back to AngryUEFI after writing out some status. And yeah, that's the red. And again, Chris did an amazing job. He actually managed to read out the physical bits on the CPU die. The basic idea behind that is you image with an electron microscope the die after very, very, very carefully removing nanometers of substrate until you reach a certain layer. And at that point, you can actually recover which bit is encoded at which location. And once you have these pictures, you can reconstruct the actual bits. You need to do some reordering and stuff, which is fun to do. But in the end, you actually can disassemble the ROM and learn more about the encoding, because your databases just grew from, let's say, 100 or 200 microcode updates with maybe 100 or 200 instructions each to thousands of micro instructions for a certain CPU. And just to show you what this looks like, I can highly recommend this web page. This is not from us, but Here you can see Zen, I think 1 CPU, and it has 8 cores. Some of them might be fused off, but they are still there in silicon. And if you zoom in onto one core, somebody actually went through annotating every component, or most of the components. A huge chunk of it is actual cache, which is not interesting to us. You have your load store unit, which is already quite complex. You have your floating point unit, which nowadays, of course, does stuff like AVX. I think AES is also implemented here, so it's really huge in comparison to other stuff. You have your classic integer ALU, which just does add sub and stuff like that. You have the scheduler. And for us, actually, we're interested in the decode unit because it contains both the fastpass decoder and the microcode decoder that we are targeting. And if you zoom in even more, you can see here, this is a microcode ROM. This stores the burned-in microcode that is used to run the CPU when it is not patched. And on top of it, you can actually see some other cells, and this is microcode RAM. This holds your microcode update while the CPU runs. Of course, this is not high resolution enough to actually reconstruct the bits, so Chris did some more work on it. And this is just some random picture we found from the process. On the right, you have an overview of the scanning electron microscope. On the left, you have a hex dump of the actual microcode. I know it's blurry, I'm sorry. And you can already see some highlights, which are knobs, because we happen to know what knobs look like, and they are fairly evenly distributed across the ROM, so it is easy to detect, okay, we got the mapping right. And on the top, you have further hex dumps. It's a whole lot of staring at bits. Also, there are sometimes readout errors, because this is a ROM checker, Chris also wrote. You have the hex dump, which is 2 instructions, 1 sequence word. On the right of that is the disassembly of ZenUtils. And on the lower left, if you click on a byte, you can actually see where this byte comes from. So the tiny red circles on the bottom are where the software detected this bit. And either it is a bit bright or a bit darker, and that means it's either a 1 or a 0. And sometimes you get readout errors. For example, we are talking about nanometers. Each dot there is a few nanometers wide. So any kind of inaccuracy is going to ruin a whole lot of bits. And to fix that, you can actually go in, there's a web page, and a few people, if they find something they don't really understand, they go there, they zoom in, you can zoom in the lower view, and actually figure out if it should be a 0 or 1. They correct it on the server. You can download the fixed version, and everybody can run it locally. To prove that we actually found what we are looking for, there is an encryption or a decryption algorithm actually inside the ROM, which is XX tier. The key for that we also have, but what we are interested in is actual algorithm. And we could go into the microcode ROM dump we had and follow each instruction. And AMD engineers really know their core. They did some really amazing stuff, essentially interleaving 2 loops and using conditional execution depending on what they need to achieve. Pretty cool to look at it, but yeah, that's how we knew we can both essentially map, if you want to call it, virtual addresses of the ROM that we can, for example, use in the microcode RAM, and to actual locations that are reconstructed from bits. Now, I wanted to show you a demo, but I woke up to this. So you can thank the Digitalisierung in Germany for not being able to do a live demo. What I can show you is how samples look like. For example, this is the AngryCAT code that just runs our Subleq example. Do the usual import. This is just a meshing code, the x64 code that we want to assemble. Won't go through that again. Then you have again the macro assembly of ZenUtils. And then you can just ask AngryCAT for a Zen 1 setup. Currently, there's only one, so it's easy enough. And you can also tell it, please reboot it. It does it by calling out to my Home Assistant instance and pulling the reset pin. And if you don't want it, just connect directly to it. And This is the entire API call you need to make. You just give it the U code you want to run in text form, the machine code you want to run in text form, and there's a feature that we sometimes use which just tells AngryCAT, do not reuse this core. So what AngryCAT usually does is if the core is not lost, which it can detect based on the response it gets, it will continue using it just so it's faster. But if you don't want it, for example, you know you just broke the microcode updater on it, which we sometimes do for test cases, you just mock it dead and it will go to the next core until it runs out of cores. For example, the Zen1 is a 6 core, so it has 5 cores we can test on, and the boot core, which we don't touch. So once it ran 5 tests, it's just going to reboot the system and wait for it to come back online. It does all of that in the background. If you really want to, you can also specify the core number, but if you don't, it's just going to pick one itself. What you get back is a response, and it can either be a failure. For example, the core encountered a page fault, a general protection fault, or it just timed out because you managed to build a microcode endless loop. In that case, it will give you the core status, which for an interrupt will be interrupt number and any register information it can get. And if not, you get back the result buffer, and in this case, we just extract 8 bytes, which happens to be the Subleq result. And then we just print it, and hopefully it matches what we expected. Now, if you want, use this, throw some random bits at your CPU. We have done a lot of stuff. We have run thousands at this point, microcode updates. We haven't managed to break our CPU yet. Google reported that when they did it, they sometimes had to hot reset a setup, but they use a slightly different method than we do, so not sure, your mileage may vary. Don't run this on a system that you can't afford to lose. It might not work. It's open source. Fork it, improve it, tell us what you did with it. I'm neither a UEFI dev, not a good Python dev, so have fun. Let us know what you might use AngryTools for, because in essence, this is not limited to microcode testing. You can do any kind of architecture testing with AngryUEFI. You need low noise timing tests. That can be done. You need to worry about caching, but you always need to worry about that. Happy to chat. You can find me around the Congress for the next few days. Just shoot me an email or try calling me. Sometimes it works. And if not, just shoot me an email and we'll find a place to meet. Everything is on GitHub. Feel free. And you can either ask me questions now, or you can just find me somewhere walking around with Nova on my backpack, and I'm usually not far away from that.
Thank you, Benjamin. So this is a great opportunity to ask questions. We do have some time. If you'd like to ask a question, please line up at microphone 1 or microphone 2 at the end there. No questions from the internet so far?
Well, if you want, I can have some backup slides if you want to know more.
I think we might have a question. Microphone number 2, please.
Did you find out how big a microcode patch can be? Is there any limit to how big you can make an instruction?
I can actually tell you the numbers for the stuff we have. Zen1. It has 64 quads. Each quad is 4 instructions and 1 sequence word. Each quad always gets executed as 1, and you can't really skip single instructions in a quad. You can knob them out. Knobs need to come at an end of a quad, which is something you also figure out at some point. So yeah, 64 for Zen1. Zen2, if I remember correctly, is a little bit bigger. Oh no, it's also 64. If you go to Zen3, I think it's 128, and if you go up to 5, it's even more, a few hundred, but I don't have that number here. But yeah, that you can actually pretty easily figure out, because if you look at a microcode update, either from the Linux kernel or from a UEFI update, which also sometimes includes microcode updates, you see how long it is. And it's always padded to the maximum length. So of course, for Zen5, for example, it's encrypted. But you just look at the length, you know how big each quad is, and then you figure out how it is. There might be some inaccuracies because some Zen architectures at the end have a config region that sets some internal CPU stage, which we don't understand, but it's just there.
Okay, thank you very much. Next question, please. Microphone number 2.
Yes. Is it potentially technically possible to run ARM code on Zen cores by editing the microcode?
You're not the first one who asked that. I heard that question before. I'm going to say not really, but in essence, you could, of course, implement a VM in microcode that emulates ARM, but you wouldn't really change the decoding logic. Back in the K8, K10 days, there was at Troopers one talk, it was called the Chimera processor, and he managed to run multiple different architectures on the same CPU via microcode. I have no idea how that worked. So maybe it's possible, but I'm just going to go with not really. And if you manage to do it, it's going to be really, really slow.
Cool. Thank you.
Thank you so much. Microphone number 1, please.
Yeah, did I see it correctly that you have microcode that can access memory directly through physical address?
Yep.
Does that bypass the MMU?
I think it bypasses the memory protections of it. I can look at my backup slides. There's actually another layer of protection that is based on physical addresses. So not every code can actually access all physical addresses. There are some are locked out. If you look at some leaks that you can find lying around on GitHub of some internal AMD stuff, you can also see that there's a mem access field that defines how the memory access is done. It can do stuff like uncached, and it also seems like it can do stuff like ignore permissions. The thing is, AngryUEFI, by default, it maps the entire 64-bit address space identity maps. If there's a RAM stick or not, it doesn't actually care. I reduced it a little bit, but I've not played around with permissions. So I think you can bypass permissions, which is actually a feature you sometimes want in microcode, but I'm not entirely sure.
Okay, thanks.
Okay, we have a question from microphone number 2.
Hi. I was just wondering if it could be used to speed up some operations that you normally run on the CPU Aura. The additional question is how fast it is. Can you run actually some algorithms inside this VM, inside this microcode?
So
Thanks.
microcode is usually only used for not performance critical instructions or really complex instructions, which usually are also not used that often. The problem with microcode is decoding an instruction already takes quite a lot of time and also power. You can actually see that if you look at the decoding engine, you have the uCode cache, which actually caches decodes of x64 instructions because it is cheaper power-wise from what we understand to actually just access the cache instead of running the entire decoder. You really might get a speed up because you can squeeze more code into your caches, in your architectural caches. If you, for example, have one single 2-byte instruction that does the equivalent of 20 2-byte instructions, you can maybe get a little speed up there, but I think you're better off just using architectural instructions that are already there.
Thank you.
Okay, for those of you watching online, may I remind you that you can ask questions on IRC and Matrix. The channel is 39C3-HAL-Fuse, and one person has figured it out. So, question from the internet, please.
Thank you for your talk. The internet wants to know whether you actually disassembled all the updates AMD made and whether you find any hacky bug fixes for hardware issues and things like that.
So yeah, we looked at some updates, mostly to just get a basic understanding of how the microcode format works, because if you get it out, it's just a binary dump, and then you need to figure out, okay, this is instruction, these are the operand fields. Most of this work was already done by Google, because we built on top of their work. They also have, which I can really recommend, in their original entries and blog post, they analyzed, I think, 2 updates. One of them for fixing an issue in some floating point or AVX instruction, and the other one actually for fixing the entry sign vulnerability on Zen 5. So it can be fun to look at it, but we haven't done that much. We were just interested in the format.
Okay, thank you so much. Microphone number 1.
My question is similar to what was asked earlier on the performance things. Have you measured, say, similar logic, similar type of micro-ops effectively that would be generated here compared to the same instructions in microcode just to see what the performance difference actually would be,
No.
if there is anything?
We didn't look at performance at all. We are just interested in how microcode works. You can do that with AngryUEFI. That's what it's built for. Just remember to either flush the cache or fill the cache, because even when we were applying microcode updates to test the timing, when we were trying to figure out the encryption or signature algorithm, we ran into problems where microcode actually had different runtimes depending on the cache state.
Thank you.
Number 2, please.
Your previous answers probably make it redundant, but have you looked at how eRMS works, like the accelerated STOSB, if it uses masks or it secretly has scalable vectors or anything like that?
I'm not entirely sure I know what you're talking about. If you're talking about stuff like AVX acceleration, that is actually done by the FPU.
I mean, x86 has rep-STOSB for memset,
yeah.
and there's the eRMS extension for it, which makes it faster.
I can't answer that. I mean, prefixes are, I don't know where they are handled. I don't know how it, for example, if you use a rep prefix, I don't know how it interacts if you use a microcode instruction after that. No idea.
Thank you.
Okay, if there are no more questions, once more a round of applause for Benjamin.